Okay, so let's move on. Plane waves. This is the very last topic for the entire semester. So at this moment, I will first explain what a plane wave is. Then I see more than 9 students here, so we can do a live demonstration. Plane waves. Plane waves are waves that propagate in a single direction. For example, I have a wave, electromagnetic wave, propagating in a z direction. A plane wave means I have a huge, infinitely large plane. And here, z is having some value of z0. Then on each location, x1, y1, z0, x2, y2, z0, whatever, x3, y3, z0, as long as you have defined your propagation direction, for example here, z, then all these 3 points have the same z value, right? So they are on the same xy plane. So whatever point you have, as long as you have the same z0 value, these locations are in phase, guaranteed. What does phase mean? Well, you still remember cosine omega t plus phi, right? We talked about this. Phasor notation. So they're in phase. They have the same phase. Okay. So that's a plane wave. So if you have a plane wave, for example, I am a plane wave, which means every point on my body are actually having the same phase. So you see an infinite plane propagating in a single direction, right? So mathematically, we might have different fields, polarization directions, but plotted, you have infinite planes propagating down to the right, okay? For example, positive z directions. Mathematically, this is from the Helmholtz equation. And if you have plane waves, the fields, although these fields are propagating into the z direction, the E fields can oscillate in both x, y, or maybe in the z directions. So now you can separate the Helmholtz equation, the vector equation, into 3 sets of scalar equations, depending on how the E fields are oriented. This one, the E field is oscillating in the x direction. This one is in y, this one is in z. Okay? We only focus on this given plane. Okay? So here you have a plane wave. Plane wave, you only have one single propagation direction, and everywhere perpendicular to your propagation direction, point by point, they have the same phase. So for this one, scalar Laplacian of Ex, here we only focus on the E field that is oscillating in the x direction, plus k squared Ex is equal to 0. What is scalar Laplacian? Scalar Laplacian is nothing more than the twice differentiation in all spatial directions. But remember, plane waves, once we have defined its propagation direction, remember, okay, pay attention. Plane waves, once you have defined its propagation direction, then the spatial variation is only that given direction. Why? Because as we said, everywhere on the x and y plane, they are having the same phase. So you don't expect to have any variations. So all the variations comes from the value of z only. So if you have a plane wave, it's almost like a one-dimensional wave, right? You only have one spatial coordinate that is varying. Of course you have the time variation, but once you have defined its propagation direction, then everywhere, all these points change in the same way as you change its z value. Okay? So this plane wave, the E field is oscillating in the x direction, but it is only a function of z. So basically, you don't have to care about this two. The function is reduced to partial differentiation to z twice of ex plus k squared times itself is equal to 0. And that solution form was already covered in the beginning of our class. You have a forward propagating wave, and you are allowed to have a negative propagating wave. Right? It is to remember, for our voltage wave and current wave on a transmission line, we expect to have forward and backward. Backward propagating voltage or current wave is due to impedance mismatch. Okay? So let me come back to the movie. Once you have the oscillating, accelerating dipole, you can have forward propagating wave and you can have backward propagating wave. Right? So when you are very far away from the dipole, this wave looks like a plane. Okay? So when you are far away from your wave generating source, you have plane waves. Now we know E field. What about the magnetic field? Well, you don't really need to go over the entire derivation. We have this equation, right? So we perform the curl operation and we know the H. So take a good look how E and H in terms of the amplitudes are related. H and E in terms of their quantity is 377 ohms in free space. Have you encountered this value in transmission line? Right? That's called the characteristic impedance, Z0 for vacuum. And if you pay attention, if you have a plane wave where the E field is oriented in the x direction, your H field must be oscillating in the y direction. So Z direction is where you propagate. Okay? So basically, a plane wave also conforms to the right-hand rule. X plus y, E field plus H. Your thumb is pointing in the propagation direction. E, H, K. Okay. So E, H, K forms itself an orthogonal coordinate system. Okay. Right. So at this point, we're reaching the very last moment. I would like to have 9 students, 9 volunteers. 9. Yeah, well, just come to the stage. Please. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9. Okay. Yeah, please do count. Okay, starting from here. Okay. Facing towards this direction. Okay. Okay, move. Start here. Okay. Okay, this is right. Okay. Good. Okay. So their hands reflect the amplitudes of the E. Okay? Now, you are looking at their hands. You took a picture. Now you're looking at them because they're stationary. They're frozen because you took a picture, so t is equal to 0. Okay? So what you see is the spatial behavior. You start from the maximum, you reduce. Okay? So this is your peak, and this is the valley, and then it comes back to the peak. So that is one wavelength. Okay? Because you have reduced this term, so you only see the spatial behavior, and you still remember k is 2 pi divided by 1. So coming from the maximum, dropping to the valley, and coming back to the maximum, that is one wavelength. Okay? Do you feel excited? You don't. Now let's do this. How to do this? Just walk to me. You're seeing a light wave propagate. Keep on going. Keep on going. Right? This field is reducing and coming up. Right? So now you see a live plane wave demonstration. All right, thank you. So you have to think. When they were walking passing me, I also did another demonstration. I froze Z, right? When they walked passing by, my hand was showing you the height of the E field. So my position was fixed. So I fixed my position. I can call that position to be 0. So I was actually monitoring the time dependence. Alright? So in the first, they were standing here, not moving, because time was frozen. So you only see the spatial behavior. You only see k. Right? When they were moving, that's omega t minus kz. Right? So the wave, how strong the field is, it just propagates at a certain speed. But for my measurement person, I was able to see how the field changed according to time because my location was fixed. Okay? So I'm actually trying to tell you how to measure a wave. Even though mathematically you only have the amplitude, frequency, and wavelength, but in order to measure these different behaviors, you need to perform different measurement schemes. Okay. To show you another movie, these are forward propagating plane wave and backward propagating plane waves. So plane waves have a well-defined single propagation direction, but once you define this propagation direction, you can also have the reverse direction. Okay? So here you have the waveform generating source. It's also a plane, and you generate a plane of electromagnetic wave into the right and also to the left. Okay. So this reflects these two truths. So whenever you feel confused in the future, just remember how your classmates were sacrificing themselves to entertain you. Okay, that's a funny catwalk, right? So let us come to the very end. If possible, I would like to have the 3 filming crews to stand up. Filming crews. Yeah, we need to thank their efforts. For the past, during the outbreak, they were here without a fear of being yeah, anyway, let's thank you. Alright, so finally, I need to thank you all for, well, staying here. I know the first 2 or 3 months, you were not allowed to come into the classroom, but finally you are. As you can see, I really think electromagnetics is covering a lot. And for me, it's not just math, but it's really having a lot of real applications. So my hoping was I gave you a lot of challenges, understanding about the concepts, and I also provided the linkage to real applications. Right? So thank you for the investment.